Welcome back to CCCS122 Discrete.
This is Chapter 6 on counting. Counting problems can be of the following kinds. Something like, how many different 8-letter passwords are there? Or how many possible ways are there to pick 11 soccer players out of a 20-player team? Most importantly, counting is the basis for computing probabilities of discrete events. And uh, probabilities of discrete events, that is the subject of the next chapter, chapter 7. So this chapter 6, in a sense, provides some preparation for the kinds of problems that you'll encounter in chapter 7. So questions like, what is the probability of winning the lottery? Now, few basics to know. Among them, the first is the sum rule. If a task can be done in n1 different ways and another task can be done in n2 different ways, and if these two tasks cannot be done at the same time, so meaning either you do it one, either you do task 1 or you do task 2, then there are in total n1 plus n2 ways to do either task. So as an example, for example, we have a department that has a free computer to give away to either a computer science student or a computer science professor. There's only one computer. It can go, either you can select a CS student or a CS professor. And let's say there are 530 students to choose from. And on the other side, there are 15 professors to choose from. Now, we can accomplish one of two things. We can give the computer to a student or a professor. So how many choices do we have of accomplishing either the task of assigning the computer to a student or assigning it to a professor? And the answer is, applying the sum rule, 530 can give the computer to any one of 530 students. And then there are 15 different ways you can give it to a professor. Because you can only do one or the other, but not both, there are in total 545 choices. Okay. And that gets us to the generalized sum rule, in which we have not just necessarily two tasks, but an m number of tasks. So let's say there are n1, n2, n3, up to nm different ways of accomplishing each of these m different tasks. And there's no way to do any two tasks at the same time, two or more tasks at the same time. And that means that there are n1 plus n2 plus n3 plus all the way to nm different number of ways to do any one of these m tasks. Then we have the product rule. Suppose that we have a procedure. Procedure means a job that can be broken down into multiple tasks. And suppose that we have a procedure that can be, for the simplest case, broken down into 2 tasks. Let's say there are n1 ways to perform the first task and n2 ways to do the second task. Question is, or actually I should say, then there are n1 times n2 different ways to complete the entire procedure. N1 options for the first task, N2 options for the second task. And just like the sum rule, the product rule can also be generalized. And so if we have not just two, but m different tasks, and each of them can be performed, can be completed, can be done in n1, n2, n3, all the way up to nm different ways, then the total number of ways you can complete the entire procedure consisting of m tasks is n1 times n2 times all the way to nm. Here's an example that uses the product rule. So how many different license plates are there that contain exactly three English letters, three letters of the English alphabet? So let's look at our options. So there are 26 letters in the alphabet, meaning there are 26 possibilities, 26 options to pick the first letter. And then there are the same 26 letters to choose from for the second letter. And the same 26 letters to pick the last letter on the license plate. Which means in total, you can pick 26 times 26 times 26 equal to 17,576 different license plates. Here's another example of a counting problem. So we have here some very simple pseudocode on the left, and it is asking what is the value of variable k after the following code has been executed. And variable k is initialized to 0 in the first line, and that is followed by 3 for loops. And in each for loop, you can see we have the same thing happening. We are incrementing the value of k by 1. Now the first loop runs from 1 to n1, and after that completes, we exit the first for loop and we enter the second for loop, which runs from 1 to n2. We complete those n2 iterations and we exit the second for loop and we enter the third for loop. The third for loop runs from 1 to n3, and that is the end of the code. So, question, what will be the value of k when you complete at the end of this code? And the answer should be pretty straightforward. We start with k equal to 0. And after we come out of the first for loop, k will be equal to n1. And with that value, we move into the second for loop, which will add another n2 to the value of k. And then we enter the third loop, which runs for n3 iterations, so which will add another n3 into the value of k. And so k will at the end of this code, k's value will be n1 plus n2 plus n3. Okay, so now let me show you a slightly similar looking, but not that similar looking, but another piece of pseudocode. This one. And we have something similar happening over here. We have a variable k initialized to 0, and inside a loop, the value of k is being incremented by 1. But this incrementation is happening inside a for loop, which is running inside a for loop, which itself is running inside another for loop. So we have three nested for loops over here. The outermost for loop runs for n1 iterations. The for loop inside that runs for, the second for loop runs for n2 iterations, and the innermost for loop, the third loop, runs for n3 iterations. The question again is, when we exit this piece of code, what will be the value of k when we come out? Now, this code is structured differently from the first example. These loops are nested, which means that in one iteration of the outermost for loop, we go in that one iteration, we go through all n2 iterations of the second for loop. I'm sorry, yes. And inside each iteration of the second for loop, we go through all n3 iterations of the third for loop. Now, we've taken basic courses in programming, and so I expect you to know that that means that k's value at the end of this code will be n1 times n2 times n3. And here's another example. We have some very simple looking code. It has an outer for loop. Inside it, we have two for loops, one following the other. So they are inside the first for loop, but they follow one after the other inside the outer for loop. So loop 2 completes, then loop 3 begins. Inside each of these two inner for loops, we print out the string hello. Same thing happening in both loops. Your job here is to find out what is the number of print statements, so the number of times hello is printed out. How many times will hello be printed out to screen? Now, to keep matters a little simple, each loop runs for exactly n iterations, n, and n. So the total number of print statements in this case will be inside the first loop, it'll happen n times, and then after that another n times. So n plus n. This is for loop 2, this is for loop 3. But all of this is happening inside the outer first for loop. And that itself is running n times. So the answer is n times n plus n. Or simplified, it becomes 2n or 2n squared. Okay, yet another example. In this one, again, we want to count the number of print statements, but the thing that we changed around this time is we played with the number of iterations of the inner for loops. So the outer for loop is still going from 1 to n, but on the inside, the second for loop, call this the second for loop, goes from 1 to I, and then the third for loop, also inside the loop number 1, goes from I plus 1 to n. So how many times is hello printed out in one iteration? In one iteration of loop number 1. And inside each iteration of the outer for loop, hello is printed out I times by loop number 2, and n minus I times by loop number 3. Add them up, i's cancel out, and just end up with n. And then, of course, all of this is happening inside the outer loop, loop number 1, which means the print statement is executed n times. This is for loop number 1, this is for loops 2 and 3, is executed n times, meaning n squared times. Okay, let's get into a slightly more interesting problem. It's still pretty simplified, but let's say we have a programming language, a computer language, and the name of a variable has to be a string of either 1 or 2 alphanumeric characters. And there are some rules, like rules in every programming language. So, first of all, this language does not distinguish between uppercase and lowercase letters. So uppercase letter is the same as a lowercase letter. You can use all 26 letters of the English alphabet in the name of a variable, and you can use the 10 digits. However, a variable's name must begin with a letter. You can't use a numeric digit. You can't use a digit in the first place. So that's another rule. And let's say that there are 5 strings and 2 single characters that are reserved by the programming language for some special use. Just like there are some names that you cannot use for your variables in programming languages. For example, you cannot give in many languages you cannot call your variable for, because there's usually always a for loop that is part of the language. So there are certain reserved keywords that you cannot use for variable names. And just like that, we're saying that there are 2 characters that cannot be used as a variable name, and there are 5 different strings that cannot be used as variable names. So let's approach it this way. So let's say that V1 is the number of strings, 1 character long, and V2 is the number of strings that are 2 characters long that can be used as variable names, which means the total number of variable names that we can come up with is V1 plus V2. A variable name will be either 1 character long or 2 characters long, but not both. So for V1, we know that we cannot use digits. We can only use letters, so that's 26 options. And let's see, what else? We have V2, the number of strings of length 2. Can use any one of 26 characters in the first position and any one of those characters plus any digit for the second position. So 26 times 26 plus 10 options. But we also know that there are 5 strings that you cannot use. So that's what this -5 over here is. So out of all of these combinations, there are 5 combinations that 5 permutations, I should say, that you cannot use. So the total number will be 26 times 36 minus 5, or 931. And now that I'm seeing it, I'm realizing that we should be subtracting 2 over here, so this should only be 24 because there are 2 characters that you cannot use as variable names. They're also reserved. It changes the value of v slightly. That means that v is equal to not 26 but 24 plus 931 equal to 955. Small typo, I'll fix that. Okay. Here's another example. How many different license plates are available if each plate contains a sequence of 3 letters followed by 3 digits? So this one's pretty straightforward. No exclusions, no additional rules like we had in the previous example. So each letter can, of course, can have 26 different characters in it. Each digit can contain one of 10 different digits in it. So that means how many options do I have? So 26 options, 26 options, 26 options, 10, 10, and 10 different options. So we can use the product rule here, and it means that the total number of possible license plates is 26 times 26 times 26 for this part, times 10 times 10 times 10 different options for this numeric part of the license plate, making for 17,576,000 different license plates. Let's do a simple password problem. So each user on a computer system has a password which is 6, 7, or 8 characters long. Each character is an uppercase letter or a digit. Each password must contain at least one digit. Question: how many passwords are there? Or I should say, how many passwords are possible? So this is interesting because of this one condition over here. How are we going to handle that? And the way to handle, one way to handle that, and the easier way to handle it, is like this. So strings, including letters and digits, and we'll just compute all possible combinations that we can make. But we have not accommodated this exception over here that each password must contain at least one digit. And for that, what we'll do is we'll subtract the option, the number of strings that we can make with no digits at all. So that this is an interesting way of, so basically finding a larger number first and then subtracting the exceptional cases. Many times in problems, it helps to approach the problem, to approach a counting problem this way. So the number of passwords is the number of 6 character passwords, 7 character passwords, plus 8 character passwords. And the number of 6 character passwords here is 366. Number of 7 minus the number that you can make with characters only, which happens to be 266. 366. It's 3 to the power 66. 2 to the power 66. Sorry, what am I doing? It's 36 to the power 6 minus 26 to the power 6. I'll fix that in the slides again. For P7, the same thing, 36 to the power 7 minus 26 to the power 7. And the same thing with P8, 36 to the power 8, and minus 26 to the power 8. You get these huge numbers for P6, P7, and P8. You add them all up, definitely with a calculator, and you get this huge number, which is millions, billions, trillion, 2,684,483,063,360 different passwords. Another very practical example is the IPv4 protocol, the IP protocol that we all use on our phones and computers and everything that connects to the internet. An IP address, IPv4 address, is 32 bits long, and it cannot just be anything. There are some rules to that. So the address space is divided up into different classes. So there are class A addresses, class B, class C addresses, which you will frequently see. There are the class D addresses for multicasting, class E addresses. So what we're going to do is we're going to stick to class A, B, and C addresses for this question. But this is basically, so each row is the structure, the rules of one class of addresses. You can see that in class A, we've got 32 bits, numbered from 0 to 31, of course. The first bit has to be a 0. After that come 7 bits that we call the network ID or net ID, followed by the remaining 24 bits, which are called the host ID. For class B addresses, the first 2 bits are fixed to 10. The next 14 bits make up the network ID, and the last 16 bits make up the host ID. And for class C addresses, the first 3 bits are fixed to 110, followed by 21 bits that make up the network ID, with the last 8 bits making up the host ID. You get the idea. So, there are some restrictions, such as the net ID. In the net ID, all ones is not available. You can't have all ones in the net ID. And for the host ID, you cannot have all zeros or all ones. That's also not available. So basically, -2 options and -1 option over here. So the question then is, the computers on the internet have either class A, class B, or C addresses. Question is, how many different IPv4 addresses can we make for computers on the internet? Okay, so let's go through this. It's not going to look nice, but I'm going to try to go through this step by step. So over here in green, we have the number of class A addresses. Over here in purple, in the middle, we have the number of class B addresses, and here in blue, we have the number of class C addresses. And how does that work? We have the first part over here for the number of net IDs we can make. The second part over here, the number of host IDs that we can make. So recall that for a class A address, you have 7 bits for the net ID, which means you have 2 to the power 7 different strings that you can make out of ones and zeros, -1 for the one option that's not available to you, all ones. For the host ID portion, in a class A address, you have 24 bits, which means 2 to the power 24 possible strings. But there are 2 options all zeros and all ones that are not valid. So those are the ones that we are subtracting over here. And we basically repeat the same thing for for class B and class C addresses. Noticing another typo over here, should be -1 and -1 over here, of course. -2 are proper, but there needs to be a -1 and a -1 over here for the host ID. Again, I'll fix this in the slides when I re-upload them. Okay. Now the sum and product rules that we've seen so far can also be understood in terms of set theory. So the sum rule, for example, assumes that we have m different disjoint sets, meaning sets that do not overlap, and the number of ways you can choose one element out of these sets is equal to the union of the cardinality of the union set of A1, A2, A3 all the way up to AM. And since these sets are disjoint, that is just equal to the sum of cardinalities of each of these sets. So the number of elements in each of these sets. And for the product rule, again, assume that we have these m non-overlapping disjoint sets. Then the number of ways you can choose one element from each set in the order A1, A2, A3, all the way up to AM is the cardinality of the m-dimensional Cartesian product of A1, A2, A3, all the way to AM, all the different sets, which is equal to the product of cardinalities of each set. So here's a simple exercise task. Task 1, construct a string of length 8 that starts with a 1. There's only one way to pick the first bit. And when I say string over here, I mean a binary string. So there's only one way to pick the first element. Just like in the IPv4 address example we just did, there's only one way to pick the first bit. But there are two different ways. You can pick the second, third, fourth, fifth, sixth, seventh, and eighth different bits. Each of these can be either 0 or 1, which means, according to the product rule, this can be done in 2 to the power 7 or 128 different ways. Task 2 is to construct a string of length 8 that ends with 0, 0. So over here, the last two bits are fixed at 0, 0. But there are two ways to pick first, second, third, fourth, fifth, and sixth bits. Only one way to pick the seventh bit, and only one way to pick the last eighth bit. So in how many different ways, or how many different strings can we construct with these rules? The answer is there are 6 different bits to choose over here. So 2, because there are 2 options for each. To the power 6, because there are 6 different positions, 6 different positions in which we have to make selections of 2 to the power 6s, 64. 64 different ways to do that. So 128 ways to do task 1 and 64 different ways to do task 2. So does that mean that there are 128 plus 64 or 192 different strings that start with either a 1 or end with a 0? Is that reasoning correct? And the answer is no, because there's overlap here. Task 1 and task 2 can be done at the same time. So when we carry out task 1 and create strings starting with the digit 1, some of those strings will have 0, 0 at the end. So for that reason, the sum rule does not apply to this problem. If we want to use the sum rule in such a case, we have to subtract the cases where task 1 and task 2 are done at the same time. So how many cases are there? How many strings start with 1 and end with 0, 0? Well, there's only one way to pick the first bit, but there are 2 ways to pick the second, third, fourth, fifth, and sixth bits. But there's again only one way to pick bits number 7 and 8. And according to the product rule, that leaves me with 2 to the power 5 2 to the power 5 options, 32 cases. Now, since there are 128 ways to complete task 1, 64 ways to complete task 2, and in 32 of these cases, tasks 1 and task 2 are completed at the same time, there are 128 plus 64 minus 32 or 160 ways to do either task. So in set theory, this corresponds to two sets A1 and A2 that are not disjoint. And so what we have to do is the elements in the overlapping region are basically being counted twice, and we are subtracting those from the sum of cardinality of A and B. This is called the principle of inclusion-exclusion. Here's another way of thinking about such problems. So let's say we want to come up with, we want to answer the question, how many bit strings of length 4 are there that do not have 2 consecutive ones, so meaning one followed by another one? Cannot have that. So how many options? So we start off with 2 options in the beginning. One of them is to use a 0 in the first bit position. If you use a 0 in the first bit position, there's no restriction on what you do for the second bit position. So maybe you use a 0 again, and a 0 again for the third bit, and a 0 again for the fourth bit. And coming back from the tail end, if you used a 0 in the third bit over here, This means you also have the option of using a 1 in the fourth bit. And as you can see, this still obeys the rule. These two options, 0, 0, 0, 0, that's one bit string. 0, 0, 0, 1, that's another bit string. Neither of them have two consecutive ones appearing. Okay, let's go back to the second bit, and we used, let's go back to the third bit, and we used a 0 in that place. We can change that to a 1, no problems. The preceding bit is a 0, so no restriction here. So we can also use a 1 in that case in the third bit position. But if we do that for the fourth bit position, can use a 0, but we do not have the option of using a 1 in this place, because that would make for two consecutive ones. Now, going back to the first bit, this can be followed by a 1 in the second bit position, which can be followed by only a 0 in the third bit position, because, again, same thing. Making the third bit a 1 would make for two consecutive ones. So can't have that. Now, since we are back to a 0, we have again two options for the fourth bit, 0 or 1. Okay. Now, all of this was assuming that we start with a 0 in the first bit position. Let's look at the other option. Starting with a 1 means the next bit must be a 0. Once that's a 0, the next bit position can be either a 0 followed by another 0, or followed by a 1, or 0 over here can be followed by a 1, in which case there's no other option but to use a 0 in the last bit position. These are all the possible, so each path that you take from the left node to the rightmost nodes, each path represents a possible 4-bit string, and it is guaranteed, the way we built this, the way we constructed it, it is guaranteed to not have two consecutive ones. So let's look at that. So basically 1, 0, 1, 0, that's one 4-bit string. 1, 0, 0, 1, that's another one. You can see how that works. If you want to count the number of possible bit strings that you can make, all you have to do is count the number of branches this tree has at the end over here. We have 1, 2, 3, 4, 5, 6, 7, and 8 possible options. And that gets us to the pigeonhole principle. The pigeonhole principle states that if k plus 1 or more objects are to be placed in only k boxes, so one less than the number of objects, then there must be at least one box containing 2 or more objects. The picture on the left, that would be this one over here, containing 2 pigeons. So, as an example, say we have 11 players in a soccer team, and that soccer team wins 12-0. 12 goals for nothing. That means there must be at least one player on the team who made 2 goals, at least 2 goals. You can distribute the first 11 goals across all members of the team, but that still leaves you with one more. that one, the 12th goal, has to go to someone who already scored a goal. Okay. If you have 6 classes between Sunday and Thursday, 5 days of the week, there must be at least one day on which you have at least 2 classes. The generalized pigeonhole principle states that if n objects are placed into k boxes, so we're no longer talking about k plus 1 objects put into k boxes, but n objects placed into k boxes, then there's at least one box containing at least n divided by k ceiling function number of objects. So if you have a class of 60 students, and at least that, and the grades that you can award to these students are A, B, C, D, or F, and you have a guarantee that at least 12 students will get the same grade. (60) divided by 12 ceiling function. Another example. In a class of 61 students, that number will go up to 13. 61 divided by 12 ceiling function. That's sorry, it's not 12. It's, we have 5 grades over here. Sorry, 5 grades. That will be 12. And 61 divided by 5 is 12 point something. And when you apply the ceiling function to that, it becomes 13. Another example. Let's say you have a drawer containing all of your socks, and your socks are of 2 different types. They're either 12 brown socks and 12 black socks. It's in the morning, it's dark, you don't want to turn on the light for some reason, and you want to pick out enough socks that you get at least one wearable pair, assuming that you want both socks to be of the same color. Meaning, you want to wear 2 brown socks or 2 black socks. Here's the question. You cannot see what the color of the socks is. How many different socks do you have to pick out in the dark to make sure you have something wearable? The answer is you have to pick, meaning you have to get at least 2 brown socks or at least 2 black socks. And you can do that in this case if you pick up at least 3 random socks. You have to pick up 3. Okay? And of help here is the generalized pigeonhole principle. Pick 3 and put them in 2 categories. So 3 divided by 2 ceiling function. The answer is 1.5 ceiling function, which is 2. Last example for this section. In a group of 367 people, there must be at least 2 people with the same birthday. There are only 366 possible birthdays. So another one, in a group of 27 English words, at least 2 words must start with the same letter. There are only 26 letters in the English alphabet. So that's the end for now. We'll move on to another topic very closely related to counting next time, which is a little more mathematical in nature, permutations and combinations.